So we're getting ready to do another lab together, and this one's called the Clathrate lab. Pretty simple on a sheet of paper, however, it seems like this is the most amount of slides that I've done for a lab so far. Go figure. Okay, so the Clathrate lab, I don't have to say a lot about it. If you've watched the pre-lab videos up to this point, you know what a Clathrate is supposed to be. And we're going to be making one in a lab, and we're going to be using one to separate two alkanes from each other. Alright, so what are those two alkanes? Well, here's going to be my first one. The first one is Hexadecane. Alright, so hexa, again, is 6, and dec is 10, and ane means all single bonds. So that means there's 16 carbons, and they are all in a straight chain as we go through. I'm not going to draw the entire thing. Again, that was also done in the pre-lab videos as well. We also want to talk about van der Waals forces here. One of the things that you'll learn about in general chemistry or organic chemistry is that van der Waals forces, otherwise known as London dispersion forces, or part of the van der Waals forces are London dispersion forces. It's just this interaction between molecules that keep them together. So typically, the longer the carbon chain, the longer the molecule, the more they can overlap. And if they can overlap as much as possible, then this really skyrockets their boiling point here. Alright, so hexadecane has a certain boiling point. You can look up that boiling point in the textbook. I mean, they give it to you right there up front and center. So if you want to know what that value is, that's where you can find it. The other thing I want to talk about, though, is that the lab tells you that you need 10 millimolars of material. Okay, so we're going to walk through this step because this could be a question that you got wrong in the pre-lab video, and you might be wondering, well, how on earth can I actually go through and calculate that value? Well, here's how you do it. So 10 millimolar, all right, so 10 millimolar. Millimolar is like milliliter or milligram. It's 1,000th, right? So I'm going to take that given over 1. This is how I set up my dimensional analysis problems each and every time. So millimolar on top and millimolar goes on the bottom, and I need to go to mole. I need out of that prefix. I don't really like prefixes that are milli or centi and so forth. So I need to get out of them whenever I can. Well, there's 1,000 or a millennia is 1,000 years, right? There's 1,000 milliliters in a liter. There's 1,000 milligrams in a gram. So there's 1,000 millimoles in a mole. I mean, that's what that prefix means. It's 1,000th, right? So it takes 1,000 of them in order to make one of those units. The problem here is that my balance cannot measure gram or mole. It measures gram. So I need to get out of mole because mole's not going to mean anything to me as a laboratory person. So mole is now on top, and the next step, mole goes on the bottom, and I need to get to gram. And in order to do this, I need a relationship between gram and mole. Well, gram and mole is related by the molecular weight of the compound, and it's 226.4 grams per mole. All right, so 226.4 grams divided by 1, because that's per mole, which is per 1 mole. I mean, that's what it's understood to be. All right, so let me pull up the calculator for you. That way you can see that. And I'm just going to key in everything just like we've wrote it down, all right? So 10 divided by 1,000, and then we're going to multiply by 226.4, and I'm going to hit enter. So this is going to give me about 2.26 grams of material that the lab wants me to use. So this is just a way for them to confirm dimensional analysis. If you look in the lab procedure, millimolar to gram using formula weight. It's all of that kind of intro general chemistry review that they might introduce in a 151 or a 152 class. So 10 millimolars over 1 because that's my given. Millimolar on top, so in the next step it has to go on the bottom. And then I need to go to mole. Well, I know that relationship's 1,000 to 1, and then moles on top. Now in the next step, that needs to go on the bottom, and I need to get to gram. And the relationship between those two is molecular weight each and every single time. So I need about 2.26 as far as grams go of hexadecane. hexadecane. Hexadecane, though, is a liquid. It's not a solid. And again, I think this is just their way to confirm the amounts and the dimensional analysis to you. Because what do? They turn around and they tell you to measure out 5 mils of 2,2,4-trimethylpentane. Well, this is a liquid. So if they're wanting me to pipette this amount, why didn't they tell me to pipette that amount? Well, another one of those reasons is one of these alkanes you're going to get in the very end. And it's very important that you keep track of masses, not just volumes. And you're actually going to see me do that with the octane number as well. So this is what we refer to as octane. However, octane, it's very confusing. Octane is really 1, 2, 3, 4, 5, 6, 7, and 8 carbons in a chain. And that really is octane. But this is a common name. And this common name goes to the 2,2,4-trimethylpentane. All right. So 2,2,4-trimethylpentane, we probably drew that as well in the pre-lab videos, but I'm going to do it again. Pentane is 5. So 1, 2, 3, 4, and 5. And then on carbon number 2 of that chain, I get a methyl group. So 1, 2, I get a methyl group. On carbon 2 of that chain again, I get another methyl group. So I'll draw another carbon. And then on carbon number 4, I get another methyl group. So if that's carbon 2, there's carbon 3, there's carbon 4, I have another carbon that is there. Of course, all of these need the hydrogens. They're assumed to be there if they're not written. So very often we shortcut this process and we just leave them out. This carbon needs 2 more, and of course that carbon needs 1 more. 4 bonds in total. All right, so that's how we draw it. If we want to discuss dispersion forces here as well, we can. This is not a straight chain molecule, though. This is a very branched molecule, and maybe in the pre-lab videos we talked about that as well, but this branched molecule is going to tremendously lower the boiling point of this particular compound. So if you compare those 2 boiling points together, that's what you're going to find out. The lab procedure is going to tell you to measure out 5 mils. We want to be exact here. You know, part of this process is our recovery. We need to report recovery on whichever alkane was captured. So it's very important that I use proper amounts and that I use proper grams. I don't want to estimate anything. What I actually use is what I want to record and report, and I want to be as exact as possible. So that is why we are going to do this using a volumetric pipette. We are not going to be using a beaker. Shame on you. We're not going to be using a graduated cylinder. Shame on you. We're going to be using a volumetric pipette that's a little bit more accurate. All right. So as far as the label information goes, hexadecane is going to be from Fisher Scientific. And then as far as the lot number goes, you're going to see that here onto the side of the label. It's 128230. So that's the hexadecane that we're going to be using in the lab. 2,2,4-trimethylpentane is going to come from a company called Acros Organics. And that lot number is also on the side of the bottle. So that's what you're going to see here. Maybe a little bit smaller for you to read. I'll go ahead and call out the lot number to you, though. It's A as in apple, and then 0254849. Again, that's A 0254849. So that is going to be the lot number for the 2,2,4-trimethylpentane. That's also called octane, so don't get it confused, from Acros Organic. Another component that we're going to need for this lab is urea. Urea is basically a carbonyl group with 2 amine groups on each side. Again, we drew this in the pre-lab videos probably. Here's my carbonyl group. That's C double bond O. And then an amine group is an NH2. So there's NH2 and there's NH2. Urea was one of the first compounds that were used in organic to disprove the concept of vitalism. This was one of the body chemicals that was made and extracted and excreted. So we thought that urea was organic at that time and that your body had to make these types of compounds to be classified as organic. However, urea was then synthesized in a laboratory. And at that point, we knew that bodies were not needed in order to make urea with. So this concept of the definition of organic began to change. The urea that we used in this experiment was from Fisher Science again. And the lot number is going to be here on the front of the label. Again, it's very tiny. I'll call it out. It's it's 3 then AD 130-123-19A. And again, it's 3AD 130-123-19 and A. What's funny, though, is that it also has an expiration date, and that was April of 2015. However, we still use these crystals. Again, we use expired chemicals all the time. It doesn't mean that they're bad, but if I was working in a regular, regulated laboratory, we would be dumping this and we would not be using it past the expiration date. General chemicals, though, they normally have shelf lives, very, very long amounts of time. A lot of people think that this is just a money gimmick from the chemical suppliers. If you can imagine, hey, we're going to sell you urea, but we're going to put a 1-year expiration date on it. So you're required to dump it and order new. As a chemical company, I'll be making a lot of money. If I was a chemical company and said, listen, this urea is going to stay good for 20 years when we ship it to you as long as you store it the right way, then you can imagine the sales begin to plummet for the chemical companies that are out there. All right, so there's urea. We've just drawn it over to the side, and it says we need 200 millimolars of that substance. All right, so I'm going to do this setup again because once more, it could be something that you got wrong. So 200 millimolar of urea, and they're going to test my knowledge to make sure I can do this dimensional analysis one more time. So millimolar on top, millimolar goes on bottom, and I need to go to mole. Well, there's 1,000 millis in a mole, and then the next step, mole on top. So mole goes on the bottom, and then gram goes here. The relationship between gram and mole, again, is molecular weight or formula weight. So that's 60.06 grams for every 1 mole. So 60.06 grams for every 1 mole. And folks, that's all there is to it. It's just 2 steps. So hopefully that one was a little bit better than the first one if you didn't know how to do it. If so, you're learning, and that's part of it. All right, so 200 divided by 1,000, and then we're going to multiply by 60.06, and this is going to give me around 12 grams. So this gives me a target value. I need to be something close to that. I just need to make sure that I write down the actual amount that we do decide to use in this experiment. So there's the dimensional analysis for urea, how we calculated the 200 millimolar amount that we needed to use, as well as the label information too. All right, so next, the last really ingredient to make this clathrate work is going to be methanol. So the methanol that we decided to use here is methanol stock. And the reason it's stock is because we have it in one of these squirt bottles that's sitting around in our lab. Typically, we like to keep these in the refrigerator to keep them cold. If you need methanol, just go get it from the fridge, bring it into the lab. It's not going to be a big deal. But it seems like every time, not every time, but it seems like often when we use methanol, we need it to be ice cold or we need it to be cold, not at room temperature. So we just made the decision to keep all the methanol in the fridge and just call it a day. And that's just what we use whenever we need it. So as far as methanol goes, meth is going to be representative of 1 carbon, and then the ol is the OH that's going to follow suit. So that makes it an alcohol. So there is methanol, or the common name is methyl alcohol. So it goes by either one of those names. One is what we call the IUPAC, and the other one is what we call the common name. So here's the IUPAC, and then here is the common. Common name uses the full word alcohol, and IUPAC does not. It only uses the ending of OL. As far as the solvent goes, the question here, it says will dissolve or should dissolve the urea. Not at room temperature, though, and not at cold temperature either. So methanol will dissolve the urea, but it's going to take a little bit of energy on your part in order to get this to dissolve, and that energy is going to come from a little bit of heat and a little bit of stirring. Okay, the lab tells you to measure out 50 milliliters. This is just an eyeball amount. You know, we're really focused on the actual amounts here of the alkanes because that is tied to my recovery. Everything else in the middle, we just get close, and that's all that matters. So 50 milliliters can be used in a graduated cylinder. We do not need an accurate volume there, or more accurate, I guess, guess I could say, than a graduated cylinder. So the label, once more, is just the stock. So I go over to the balance. Here's a picture of the balance, of course, and I'm going to tear it out. So I'll push the tear button. I want to make sure that my doors are closed and the top door is closed as well. I don't want to see any fluctuation. If I do, then this means that my balance needs to be calibrated, or I need to clean my balance, or something is on the balance that's causing these fluctuations to occur. Small fluctuations are okay though, but larger fluctuations are going to be a problem, and it's a sign of a larger problem mechanical wise inside of my balance. So that's something I just want to make sure of, that I pay attention to. All right. Also down here at the bottom, notice big bold, big letters, ensure that the balance is clean. I want to make sure that the balance is clean before and after I use it. It seems like this is always a problem. People go over and they pour their stuff on a weigh boat and they walk away and they never clean up after themselves. You know, it's like sleeping at somebody's house as a visitor and you refuse to make up the bed. I mean, why do you do that? All right? Manners, people. Manners. So take the sheets off, at least, because you know they're going to wash them, or at least I hope they're going to wash them. So here's the balance. 0.0000 grams. I'm then going to put a flask on it, and I'm going to get the mass of the flask. Now, granted, I might not need that mass, and that's okay, but like I've told you before, I always take the masses of everything, even if I don't need to use them. At least I have them. So that way, if I forget about something, or if I don't fully understand what I'm doing, and I do need those masses in the end, I've not ruined my entire lab from that point. So I always record the masses of everything that we use in the lab. So there's the mask of the Erlenmeyer flask, and it's 85.9674 grams. So that is the empty flask at this point. Nothing's in it at all. So now I'm going to tear it again, so that way I can get a direct readout when I do begin to add my alkanes to this Erlenmeyer flask. All right, so I've pressed the tear button, 0.0000 grams one more time, and it is stabilized and it's ready for my additions. So the very first thing that I add first is going to be the hexadecane. So again, it doesn't have to be exact. I just need to get close to the target amount that they told me. And as long as I write down the mass, then I'm good. So I measured out hexadecane, and I ended up with 2.3972 grams of hexadecane. So right now, hexadecane is in that Erlenmeyer, and we're going to be making a Clathrate, and we're going to determine if it picks up the hexadecane. And if so, how good is my recovery going to be? Meaning, was I behaving myself when the transfer steps came around in the lab experiment? So, doesn't need to be exact. I just need to write down the exact amount that I have used. So get close to what the book tells you to, but don't go overboard. Don't shortchange yourself, and don't go over that amount extremely high either. All right? Okay, so now I'm going to re-tare it. Hexadecane's in there. I re-tared it 0.0000 grams one more time. And now I can add my 2,2,4 trimethyl pentane to that flask in order to get a mass. Again, I don't think the lab experiment is going to tell you to do this, but I always try to get masses of everything that I use, including the reagents when possible. So it told me suspiciously to do the mass of the first one. Why didn't it tell me suspiciously to do the mass of the second one? Well, I just want to make sure that I don't need it. So what I do is I re-tare it. I go and I get my volumetric pipettes, and here we have an assortment of pipettes that you see in the drawer, and I reach for the 5, which is 5 milliliter. I take the pipette out, and up here at the top of the volumetric pipette, you'll see the etched marking, and that etched marking represents the total volume that's stamped on the volumetric, and in this case it is 5. So I need to suck solution up in this volumetric pipette until I get the bottom of the meniscus, which is the bottom of that curvature, at that line, and that is 5 milliliters exactly. All right. Now they tell me to use 5 mils, so I'm measuring out 5 mils as close as I can, and pipettes do a much better job than beakers and graduated cylinders. I often say beakers and graduated cylinders are skanky. Don't use them. They're great to drink out of. They're great to get an eyeball as far as volumes go. But if you really want to play the game, you use pipettes whenever possible, if exact amounts are going to be important. So exact amounts, 5 mils. I suck up liquid into that volumetric pipette. When I get to the top of that etched marking with the bottom of my meniscus, I take the pipette over to the balance and I deliver that 5 milliliters into that tared container. All right. Now, a couple of things that I want you to take away with a volumetric pipette. You will see 2 stamps on them. One is TD and one is TC. The ones that we have are TDs. TD stands for to deliver. So when you release the suction on the volumetric pipette and you allow this liquid to drain into the Erlenmeyer flask, TD pipettes are going to deliver the amount that is stamped on the pipette, which means you do not blow them out. Okay, well, what does that even mean? Well, that means some people have an issue because there's a little bit of volume that's left over in the tip down below. And they think that that volume needs to go out and into that flask. And you do not do that. You do not blow out those volumes of a TD pipette because they are meant to deliver. Now, TCs mean to contain. Those you do blow out. Okay, there's the difference. So a pipette that is labeled TC is containing 5 mils. It might not deliver 5 mils, but it contains the 5 mils. And that means that any residual that you'll have down here in the very bottom, you do blow those out. Maybe with a pipette bulb, right? Just give it a poof of air, and that air will knock any residual liquid out of the pipette. The TCs, you have to do that with. The TDs, you do not. They are structured in a way to deliver the appropriate volume. And we always use TDs. They are also stamped on the volumetric pipettes whenever you decide to use them. So you will see a TD or TC up at the tops of them, depending on what lab and what class that you're in. All right, so 2,2,4-trimethylpentane, 5 milliliters goes into that tared flask, and that mass is going to be 3.4187. So 3.4187 is the mass of 2,2,4-trimethylpentane. All right, so we've used those 2 reagents. We've got masses of each one, and now it's our job to mix them together. So this is the image of the flask after those 2 alkanes, and they are alkanes. They were all single bonds. So those 2 alkanes were mixed together, and there's your observations. So if you need to make observations of the mixture, there you go. Now this is before the urea is added. It's before the methanol is added, of course. These are just the 2 alkanes that are mixed together with each other. So if you do need those observations, there you go. That's what they look like. All right, so now I'm going to go back to my balance, and I'm going to go to the weigh boat. I'm going to measure a weigh boat. So I've tared the balance again, 0.00000, and then I put a weigh boat on it, and that weigh boat is going to weigh 1.6405 grams. Again, I might not need that mass, but I at least did it. I'm going to write it down so that way if I do need it later on, then I've got it. So there we go. There's the mass of the weigh boat. So the reason that I'm doing a weigh boat now is because I'm working on the urea amount. I'm getting ready to measure out that urea and mix it with my methanol to make my solution with. So I'm then going to tear out that weigh boat, make it read 0.0000 grams, because I now know I need about 12 grams of urea in total, right? So this will allow me to get a direct read if I tear it out. So then I'm going to go back to my urea container, bring it over to the balance, and then I will pour that urea out into the weigh boat and get something close to 12. Again, I want something close, and I'm going to write down the exact amounts that we used. So 12.1417 gram of urea is what we use in this lab. If I want to zoom in and give you a close-up of the urea, this is what it looks like, folks. It's a little different than some of the other stuff that you've seen so far in the lab. These are what I would call more like a pellet instead of a powder. However, they're white, you know, and they are somewhat crystalline. If you do touch them with your fingers, I mean, you'll get white powder and stuff on your fingers if you do that. But these really are in a pellet form and not just a powder form. So just a different observation that you can write down in a lab notebook, because it is somewhat different than some of the other things that we've seen so far in the course. So I'm going to transfer all of that urea over to a beaker. I'm going to have to make a solution with this urea, and it's going to tell me to add methanol to it. So I've transferred all of the urea over to the beaker. I'm then going to go back to my stock methanol, and the lab tells me to measure out 50 milliliters. So that's what you're seeing here in the picture. Here's the 50 milliliter mark. The bottom of my meniscus is about on that 50 mil mark. Again, this is not exact. I need to be fully exact with my alkanes, but not necessarily everything else that goes into this. So as long as I'm close, we're good. So 50 mils in total, and then I'm going to dump all of the 50 mils into that beaker that contains that urea. And I'm going to slowly mix these two things up. Now, in the beginning, here's the problem. It's not going to dissolve very well. So the lab directions are going to tell me to stir this solution. All right, so that means I need to get a magnet. So I've got a magnet now, and I've also put on gloves because I'm working with methanol, and I don't want methanol to absorb through my skin because it can be poisonous. It can make you go blind if you're not careful, and I'm working with a lot of it. So now I've put on gloves. I've actually wised up and put on a pair of gloves to protect myself. All right, so there's the magnet. I'm going to put the magnet down into that container, and then it's also going to tell me to warm up this solution. So here's the picture of it in the beginning of the mixing stages. So it's right now on the hot plate, and it's getting warm. It's not hot yet, but it's getting warmer. And you can automatically see an observation change that begins to happen at this point. So I am stirring that solution. I am slowly heating that solution, but I don't want to get this solution so hot that it begins to boil off my methanol. Because if that begins to happen, then I don't really have 50 milliliters of methanol anymore, do I? So I want to make sure that I take it slow. Do not evaporate the methanol off, because you don't want to end up with 30 mils when you were supposed to use 50. That doesn't make any sense. So take it slow, don't go crazy with it, and you want to slowly heat this up until the urea is dissolved. And at that point, you need to take it off. Okay, so for that reason, I don't really need to record any type of temperature. And that's what I'm kind of getting down to. We just need to heat it enough so that this stuff will dissolve on me, and then I just need to take it off of the hot plate. All right, so here's a video of the urea in the mixing stages that I'll play for you, so that way you can maybe make some observational changes there as well.
Guys, the lab directions will tell you to take the urea, mix it with methanol, and put it on a hot plate to stir, and you can see why. The urea is not really dissolving in the methanol that well. However, under warm methanol conditions, it will. So over time, this urea is going to break up, it's going to dissolve, and it will go in solution. But here you're seeing my urea methanol mix on a hot plate with a stir on the inside.
Okay, I know. Nothing exciting, but, you know, at least I'm doing my job and giving you the observations and allowing you to see every step of this procedure along the way. Now, I know that will turn into a long videos and, you know, an hour or more of your time, but at the same time, I don't want you to miss out on any steps along the way either. All right, so there is the urea mixing together. After I heat it, it does begin to clear up, and this is what I end up with. So the directions tell me to go to 55 or 60. Don't boil it. Honestly, I never put a thermometer probe in it because I knew that I wasn't going to go that hot anyway, because I was taking my time with it. So I just allowed it to stir, allowed it to be warm on the hot plate until this began to happen. So when that cleared up the way that it did, I can see my magnet is still in that beaker. I just took it off and allowed it to cool a little bit before I went on to the next step. All right, so I'm going to take my Alkane mixture, and here it is. So those are my two components, which is Hexadecane and 2,2,4-trimethylpentane. And now I'm going to mix that urea with methanol, the entire thing, all 50 mils, the entire thing into that Alkane mix. So in this next video, that's what you're going to see me do.
So this tells me to add the Alkane mix, which is in the Erlenmeyer flask, to the warm methanol with the urea that's over here to the right-hand side. So that's what I'm going to do, and I'm going to show a video of that process just so you can make an observation change if you want. So I'm going to quickly add the Alkane mix or Alkane mix to the urea mix, and there you go. That's what it's doing. So it then tells me to rinse out that Erlenmeyer flask with a little bit of methanol. That's what I'll do. I'll let this process just kind of sit out for a little bit, and it tells me to cool it to 30 degrees, which is room temperature. So at 30 degrees, I'll then put it into an ice bath.
Okay, so it somewhat cut me off. I'm getting ready to put it into an ice bath once it gets to 30 degrees. But notice the observational changes weren't very exciting in the beginning, were they? However, after 1 or 2 minutes, this is what begins to happen. Now you can really see a change here. It's a beautiful change. I mean, look at those, right? So this begins to happen at 12:26 p.m. on that particular date that I did it. And I do have a video that shows you a little bit of movement, right, with that precipitation as well.
So this is my Alkane mix with the methanol and urea. After a few minutes, 5 minutes or so, this is what I'm seeing in the beaker. So that way you can make your observations as you see fit. But that is what this process begins to look like. So quite different from what it did in the very beginning.
Okay, so I want you to pay attention to the observations here. The very first thing that I will say is look up here. What do you see? All right, so that area is going to be somewhat important because it does look like I do not have just one layer here. It looks like there's something that's separating up here on the very top. It also, of course, looks like there's a lot of solid precipitate that's beginning to happen, and they are very long needle-like crystals that begin to form out of that beaker. Those crystals, that's the clathrate that's forming. So when this begins to happen, the urea has now surrounded one of those alkanes. I don't know which one it is yet, but it's one of those alkanes. And when it surrounds those alkanes, it is forming a cage around them, and it's trapping them, and it's pulling them out of solution. And that is the presence of the white crystal that's very long and needle-like that you're seeing in this image. All right, so at 12:29, here's an observation. It's beginning to change. I start to see more and more solid, don't I? All right, so here's the picture at 12:26, and then 3 minutes later, this is what I will end up seeing, okay? And then 12:32, a little bit later, this is what I end up seeing. So once more, you can make your observational changes as you see fit. Write those down into your lab notebook so that way you get credit for those. All right, so in the next step, it's going to tell me, let it cool. When it cools down and gets to 30 degrees, you then want to put this stuff in an ice bath. So I go to the freezer. I go through and I'll get some ice cubes out of the freezer. I go in and prepped those. And if I pre-read my lab experiment, I'm also going to realize that I need some ice cold methanol as well. So I take the methanol bottle and I'll put it into the freezer until I'm ready for it. So this will help ensure that it is super ice cold. And I'll show you what happens because it happened to me. It wasn't as cold as what it needed to be in the separation stages a little bit later on. All right, so I go and finally I bring out the temperature probe. I put the temperature probe into my Alkane beaker. So that's the Clathrate with the alkanes and the urea and the methanol. And that solution was reading about 30.2 degrees. So this was okay. It said that once it reaches 30 to then put it into the ice bath. We don't want to shock it with the ice bath temperature because I could get some impurities and some other things that begin to fall out if I'm not careful. So again, I want to take my time. Patience is a virtue, and patience is going to be a virtue here as well. All right, so I then take that beaker, the entire thing, and I dunk it down into some ice water. And that temperature is going to initially read 28.7, and this begins to happen at 12:37 p.m. So this will give you a time stamp at least to let you know how long I did keep it in an ice bath before I took it out. The directions do give me a time kind of duration that's preferred, so that is one of the reasons that I write down the times whenever possible. All right, so about 10 minutes later, 12:49 is when I begin to take this out. The temperature readout was 14.8, so it did go colder, but it didn't go what I would say freezing. So whenever we use an ice bath, it's sometimes, very often, we would see like 5 degrees or 8 degrees Celsius. This had a little bit further away to go, and you know, part of that reason is just really due to the ice bath temperature itself. My ice was melted at this point, but you know, this is cold enough for what we need. At least that's what I thought. So I took it out and I'll just kind of let it rest onto the lab bench. And here's the observations after the ice bath is finished. So you can make your observations here, write them down into a lab notebook if you need them, but from that picture you can clearly kind of explain what has happened at this point. In addition to that, I also have a video as well. So let me play that.
Okay, so this is my Alkane after it has been inside of the ice bath for at least 10 minutes. I kept it in there a little bit longer just because my methanol that I need to rinse with was not cold yet. So I just left it in the ice bath, no big deal. Nothing's going to hurt it. This is the product that I need to filter, and what I've got down here below is, of course, a Buckner funnel. It seems like the Buckner funnel has been our friend this semester so far, hasn't it? So I'm just going to reach over, I'm going to turn on the water in order to create the suction. I'm then going to squirt the filter paper that's on top of this Buckner funnel with ice cold methanol, because that's what I need to rinse my crystals with. And then I'll just slowly pour this white solid that's inside of this beaker through the Buckner funnel. Slowly.
Okay, again, exciting stuff. I know. You don't have to tell me. All right, so we need to go through and we need a filter. You saw the Buckner funnel that was in the image. So whenever we use a Buckner funnel, of course, we're going to have to use filter paper. So here's the filter paper that we decided to use. This was Wattman grade filter paper, 50 millimeter size. So these perfectly fit in our Buckner funnels. And very often, you might be required to write down the label information from material like these consumables and supplies as well, not just reagents, but the other materials that are used. So I'm going to go to the balance. I'm using a piece of filter paper. I probably need the mass of that filter paper, don't I? Just in case I need it a little bit later on. So I tear out the balance, and this is me tearing it out before I put the piece of filter paper on it, of course. And then once it reads 0.0000 grams, guess what? I put a piece of filter paper on it. So here's the filter paper that's on top of the balance pan. 0.2059 grams. So this gives me the direct mass of that filter paper. You know, I never want to take a chance of having too much product. If I get too much product, my little piece of filter paper is not going to hold all of it. And because of that, then I need to put it into a bigger maybe plate or watch glass in order for me to measure the mass of everything. So that also includes the mass of the filter paper that I'm using, because my crystals could stick to this filter paper and there's no way for me to scrape everything off. So I go ahead and get the mass of the filter paper, and that's what it is. All right, so here's the observations of the Clathrate. It is a 2-component mix, of course. That 2-component mix, my urea has captured 1. I need to figure out which one it has captured, and the other one is still swimming around in solution. So in the filtration process, what's going to happen is that the one that it did not pick out will go through the filter paper. All of my methanol and unused urea will go through the filter paper, and then my urea clathrate, which is the solid, will stay on top. And that's the one, the alkane, that it has captured. So I need to figure out which one did it pick out. All right, so Buckner funnel, like usual, I always want to do what we call seat the filter paper, which means you get it wet. You don't just put a dry piece of filter paper on this Buckner funnel and turn it on and start pouring things through. If you do not seat it, it doesn't completely seal the holes in the Buckner funnel, and your material could escape through those holes and go to the filter flask that's down below. All right, so the way that we seat the filter paper is I use some ice cold methanol to rinse the filter paper with in the very beginning when the aspirator or the suction is on. When I do that, it makes the filter paper wet. That wet filter paper will stick to the bottom of the funnel much better, and it will help ensure that all of those holes are completely sealed up. And then I'm ready to pour my alkane clathrate through. So I'm going to slowly pour that clathrate through the funnel. I don't want to dump it in all at once. I have the tendency to, if I go too quick, to stop up the holes, and then it takes forever for it to filter through, and I just don't want that to happen. All right, so then I begin to see a problem. As I'm filtering, I look into the bottom of the filter flask that sits down here below, that's capturing all of the liquid that I don't want, and I'm starting to see some cloudiness that happens. And then as I look at it closer and closer, that cloudiness is turning into a solid precipitate. Which means, number one, I didn't let it cool enough. Or number two, right, there's always a couple of ways that I could have messed up. The filter paper wasn't seated the proper way. Or number three, I just didn't give it enough time. One of the three things are happening. But this is no big deal, because the only thing that I'll do is that when I get to the end of this process, I'll just take whatever's left over here in this flask. It's clean. I didn't do anything to it. And I'll just re-pour it through the Buckner funnel. And then that way I can capture those extra crystals that did form in the very bottom. All right, so once I pour all of my solution through, here's my beaker. And I have some residue that's left over in that beaker. I need that residue out because this is the clathrate that's here. And that clathrate has my organic unknown component. And I want to make sure that I transfer all of that over. All right, so here's the bottom view of that beaker. As you can tell, there's quite a bit. I can also still see the magnet that is there as well. That magnet is eventually going to have to come out. I'm going to have to rinse that magnet off because there's going to be crystals that are going to be attached there as well. All right, the side view of that beaker, this is what it looks like. There's quite a bit of crystal, I think, that you can tell now that's left over in that first initial transfer. So I need to continue to rinse out that beaker, and I need to continue to transfer that residue or that solid over into my Buckner funnel. As I look down at the filter flask, I'm starting to see more and more solid, even more so than from the very beginning, in that filter flask that's beginning to fall out. So I'm then going to have to filter that through and rinse that as well if I'm not careful. Okay, filtered clathrate. This is what the stuff looks like on top. So again, you can make your observational changes, write down what you see, describe the crystals. That's what the lab book is going to want you to do. And then I'm going to rinse those with ice cold methanol, and that's what you're seeing here in this picture. And it has to come from the freezer, right? Refrigerated is not ice cold. Refrigerated is refrigerated. Refrigerated is not ice cold. So the reason they say ice cold is because alcohols normally do not freeze. So if you ever put ethanol, aka drinking alcohol, in the freezer, you're going to see that unless it has tons of sugar and other additives, that alcohol is going to get super, super cold, but it's going to stay as a liquid. And methanol does the same thing. All right, so I'm going to rinse, rinse, rinse. Clean off all of those crystals, make sure that nothing's there. I'm then going to take the ice cold methanol and I'm going to rinse out that beaker for rinse number 2. And I use about 25 milliliters in order to do that. So I swirl and I dump, and then when I do that, I see that less crystal is left over in that beaker, which is good. That means that that transfer step happened the proper way. However, I'm still not happy with it. So I'm going to go in and I'm going to try to get some more of that crystal residue out of there. I'm going to use another 25 milliliters of ice cold methanol, and then I add it to that beaker. I rinse and I dump. And when I dump, this is what I see left over in that beaker. So it's much better than what it was before, as you can immediately tell. I feel really good about the transfer after that point, so I do not worry with any kind of small remnant that's left over behind. I'm then going to empty the filter flask that's down below. I just really switch it out for a new one, and then I take that filter flask that had all of that extra precipitate in it, and I transfer it over to a beaker, so that way it's easier for me to pour out. When I do that, folks, this is what was left over right there. That's how much product escaped through my filter paper and went down into the flask that sits below. And all of that stuff would have been dumped if I was not careful, and all of that would have been product that would have been lost. So I've got a video here that explains that process a little bit more.
Okay, so this is my second filtration attempt. The reason I'm doing this again is because all of this actually went through my filter paper the first time, and I caught it in the filter flask down below. So all of this is product that I do not want to lose, and if I didn't catch it, all of this would have ended up down the drain, and my percent yield would have went, boom, right? So I'm going to filter this through again for a second.
Okay, so again, it cut out a little bit, but I'm going to filter it through a second time. This is what you're going to see at the observations as far as what went through the filter flask. And once more, I think that you can kind of back me up. There is quite a bit of product there, and that product has to be saved. It has to be reclaimed, so I'm going to have to filter that one more time. So I take it, I dump it through, I still get a little bit of residue that's left over in that beaker. So of course, what do? I need some more ice cold methanol. So this is the pour through first, and this is what's left over. So that's from the top view, this is what's left over from the side view, and this is a view from the bottom. Okay, so I'm going to add ice cold methanol, again another 25 to 30 mils. I give it a good swirl, and then I give it a good dump into the Buckner funnel. And here is the top view now, looking down through the beaker. You can still see a little bit of remnant that's around these edges. You know, I tried to get some of that stuff off. I just wasn't able to do it. And sometimes it can be a little stubborn that way. So here's the side view. Notice there's no crystal. What you're seeing here are maybe like water droplets and condensation, because this stuff was ice cold, remember. But I'm looking for crystal here. There's very few crystals that are left over. And then here is just a bottom view looking up toward the top, and once more you can see that a lot of those crystals are just gone at this point. So I felt really good about that. One more time, I look at this filter flask, and this is what I see. Now, I know what you're thinking. Oh my God, he's going to have to do it again. Well, no, not necessarily. The reason that I did not filter this again is because I didn't see any solid. Now, I saw cloudiness, and that's okay, but I did not see any solid formation. I saw solid formation the last time. That's why I had precipitate. That's why I had to refilter, because I needed that precipitate. This stayed as a liquid, and that's okay. As long as I'm not seeing solid form, then I can ensure that I've got the majority of what I needed out. However, if my percent yield is low, then there could be a little bit remaining in this step, and I just didn't have the patience to wait for it even more so. So, is there some left over? Could there still be some more that filters out? Maybe. Maybe. But it could take an hour. And I'm not going to wait here for an hour in order to do this. I feel really good about the amount of quantity that I have in that Buckner funnel. And then in addition, like I said, there's no immediate formation of any solid that's down here at the bottom. So maybe it will never precipitate out because there's nothing to precipitate out. It's just a cloudy solution. So once more, I don't want to waste my time just to test that hypothesis, right? Okay, so here's the Buckner funnel on top. That is what the Clathrate looks like after it has filtered through. Okay, so once again, you can go through, talk about the changes of the Clathrate, tell me what begins to happen, and then what I decided to do is I let this run 30 minutes. I let it run, just pull air through it, kind of help dry out that Clathrate a little bit, and within that 30 minutes, I went back, turned the funnel off, and then I took another look at the filtrate that was in the filter flask down below, and this is what I saw. Okay, so notice again, it's clearing up a little bit on me. There's no precipitate that is formed, and it almost looks like a little globby layer up here on the top, doesn't it? Look at that. Well, this would make sense because that could be an alkane, which is organic-y, and methanol is polar. It's more like an aqueous solid or solvent. And that aqueous solvent and this organic-y alkane are probably not going to mix very well. So this kind of makes sense because my urea should have captured one of the two, and my other one should have went through the filter paper into the flask down below, and that's what I'm seeing right there. So that all makes sense to me. Very good sign that it did capture one and it didn't capture both, because I see a somewhat organic-y layer in this aqueous phase. All right, so now let's talk about the Clathrate. The lab directions are going to tell you not to put this into an oven. All right, do not put it in an oven. And the reason is that it destroys the Clathrate. So because of that, it really does tell you you have to leave it overnight. At least you have to leave it overnight. So I came back in on the second day. 6/19 is the date. And that 6/19 day, I went to the balance, and hopefully my Clathrate has dried at this point. And I zeroed out a balance, 0.0000. And then I take a watch glass. You can see that on the balance pan. It's right there. And I put it onto the balance in order to get a mass of the watch glass. So the mass of the watch glass is 53.8701. The reason that I did a watch glass is because I have a lot of crystal. Tons of them. That filter paper is not going to hold everything. So I'm going to have to scrape those crystals out. And I'm going to have to put them on something else. And I need the weight of that, so that way I can get the weight of the crystal that has formed and my Clathrate that's been dried. So that's the purpose of the watch glass here. And watch glass, great job for those. I mean, that's one of the reasons that we use them. So 53.8701 is the mass of the watch glass. I then go back to my Buckner funnel, and I take a scoopula and I scoop out some of my crystals. This is what the dried alkane Clathrate looks like. Folks, there's tons of that in the funnel. Tons of it. And again, the filter paper's not going to hold it all. So I need to be able to scrape that over into a watch glass, and that's why I did the mass of it. So there is the observation of the dried Clathrate if you need that for any purpose. I also have a video of that dried Clathrate, so that way you can see that maybe in a different point of view. So here we go. Folks, so this is what the Alkane product looks like as far as the Clathrate's concerned. So I'm about midway through. I'm just going to give this watch glass a very quick turn, so that way you can make observations of what you see in front of you. It's somewhat out of focus, but that's because I'm zoomed in quite a bit. And there's stuff on the back side and the front side of the watch glass. So this is what the Alkane Clathrate looks like. I'm getting ready to dissolve this crystal.
and free up the alkane that it has captured. So we're going to figure out which one of the two did it actually reach out, grab, and decide to trap into its crystal lattice here.
Okay, so these are kind of important observations and numbers because part of your lab procedure is going to ask you to calculate the theory yield of your clathrate. All right, so that's what our clathrate is right here. All right, so that's why we did a mass of it. That's why we dried it. That's why we went and put it on a balance. And now it's going to be my job because there is trapped alkane in those crystals. And I need to dissolve those crystals and free up that alkane at this point. And then that way I can do a measurement of the alkane as well. Not just the clathrate compound, but just the alkane on its own. So that's going to be a different measurement toward the end of this experiment. All right, so I still see a little bit of residue that's left over in my Buckner funnel. You can clearly see that not all of that was transferred over for me to get a weight. Again, I tried and tried and tried, scrape, 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 but the more I was scraping, the more that was just getting left over. So that was going to be pretty much stuck, and it was being kind of stubborn. So I had a good enough amount, I felt really good, to be representative of what we ended up with. This crystal was just super sticky to the sides of that Buckner funnel, and there was nothing really that I could do with it. All right, so then I go back to the balance. I then tare this balance out one more time, 0.0000 grams. Make sure all the doors are closed, and I'm getting ready to take my crystal and the watch glass and that filter paper that I used, and I scrape all of that onto that watch glass, and I get a mass of it. So the mass of all three of those components, it's going to be 59.9603. All right, 59.9603 grams represents the mass of the watch glass plus the mass of the filter paper that we used plus the mass of the clathrate that was also formed and dried, because all of this took place really the next day. Okay, so now I'm going to take all of those clathrate crystals, and I need to dissolve those. So I'm going to transfer those. Yes, I know, another transfer. I'm going to transfer those again to a beaker. And that beaker is going to get some solvent that's going to dissolve those crystals up for me. So that's why I'm having to transfer it over once more. Well, through the transfer step, I do have a little bit of remnant that's left over on the watch glass, but no big deal. It doesn't look like a lot, but I at least did take a picture of it to show you that we probably did lose some of it at this point yet again. That's the problem with transfers. Every time you do a transfer, you're going to leave some stuff behind if you're not careful. All right, so all of that stuff needs to be dissolved in that beaker. So over here to the right-hand side, you're seeing the alkane clathrate, and the lab directions are going to tell me how to dissolve it. It says use hot water. That's all that you got to do. Use hot water. Okay, so I'm going to take a hot plate. I'm going to put a beaker with some water in it. I'm going to heat it up. I just turned it up halfway, a little more than halfway, and just let it crank up some heat and let it get warm. I didn't measure any temperature. It just says hot water, and then it said add the hot water until all the crystals get dissolved. So I'm not going to take this up to boiling by any chance. I'm not going to take it up to boiling, but I am going to get it to where it starts to steam and where it's going to be uncomfortable for me to hold for a long period of time. Well, one of the ways that I'm going to take care of the residue is that I'm going to take that Buckner funnel that still had some remnant there. I didn't get a mass of that remnant, but that remnant still had some alkane in it, and that alkane I am going to have to get a mass of at the very end. So I said, well, why not? Why not take some of that hot water and squirt it through that Buckner funnel just to make sure that I can get all of those crystals out as well. And that's exactly what I did. So I took basically some warm water over to the side. I sucked up some in a disposable pipette, and I just slammed it inside of this Buckner funnel. You can see the plastic pipette here that I'm holding. So inside of this Buckner funnel, and all of that is going to be rinsed and washed through. So here is the amount of liquid that I used for that transfer. And I'm looking at like 20 mils maybe, give or take a little bit. And then over here to the side, to the left, I've got more hot water that I'm going to be using to dissolve those crystals with. All right, so I add that to what was already there. It did dissolve most of the crystals, but here's the observations of that solution that you can take away. The lab directions said fully dissolved. Okay, and I'm not happy with this. What I'm looking at right now is a cloudy solution that's down here, and I'm not going to say that that's fully dissolved. I think that we can do a little bit better than that. So I'm going to heat this solution up. Now, it told me hot water. I don't want to go hotter than hot water would get, which is 100 degrees Celsius. So what I'm going to do is I'm going to take this beaker that has the partially dissolved crystal in it. I'm going to put it into a larger beaker that has hot water in it. And then I'm going to put that combo on the hot plate. And this started at 12:50 p.m. Okay? And I'm just going to heat it. I'm going to heat it up. All right, so here's a video of that process.
Okay, so what you're seeing here is a boiling water bath. One of the reasons it tells me a boiling water bath is because water doesn't boil greater than 100. So this helps ensure that I do not add too much heat to this clathrate that's getting dissolved on me. So that's what you're seeing in the larger beaker. You see a level of water, and that's getting heated up, and it's at the point of boiling at this point, and it's helping dissolve those crystals on the inside beaker that I have just sitting into the boiling water bath.
Okay, something that I don't know if you realized in that video or not, but you could actually see a second layer up here. That is a layer of liquid that's beginning to form on the surface of that inner beaker. And then down here is that cloudy, more aqueous, because we used hot water, didn't we, layer that's forming on the bottom. So that's just kind of an eagle eye onto the observations inside of that inner beaker there. And something that we can note, because I do see really a separation of a layer there. From the top down, this is what that solution begins to look like as I heat it. So as you can tell, it's getting clearer and clearer and clearer over time. All right. Finally, notice any observation changes here. This is toward the end of the process. And that end of the process, I think it has cleared up quite a bit, especially from where it once started. All right. Then the directions tell me to cool it. Now that it has fully dissolved, you're going to take this beaker out. You're going to let it cool down a little bit. And again, what you see here, I think is very evident at this point. So make that observational change in your lab notebook. And then it tells me to put it into an ice bath. So we want it not super hot. Okay, and the reason for that is the next step, and I'll tell you about that next step in just a second. But the ice bath is prepped here. That's what you're seeing. It's just a beaker of cold water with an ice cube in it. That's all. And we want to take our time with the Alkane Clathrate. We're going to let it cool down first before we put it into the ice bath. So this began at 1 p.m., and then at 1 p.m., I put the beaker that had the Clathrate in it in the ice bath, and I just let it sit out. I let it chill. I walk away, and I come back a little bit later. All right, when I come back, what I see on the very top is a solid that began to form. Now, this is kind of weird, isn't it? Because one of my alkanes was a liquid that we measured on a balance. The other alkane was a liquid that we measured with a volumetric pipette and a balance. And now I get a solid. Well, that's because this is cold, and this means that whichever alkane this was, there's a chance that my temperature is so low that it has frozen it, just like water freezes. Alkanes and organics can do that as well. So the directions tell me you could see a solid that gets formed. And I did. And this was a very good sign that I was toward the end of the cooling process at this point. So I felt really good about what I saw. This was not alarming by any means. So I'm just going to have to kind of take care of that in the separation stage. All right, so here's a video of the ice bath and toward the end of that process.
What you're looking at right now is the Clathrate after I've kept it in the ice bath. So I'm just going to take this thermometer, and you can see how it has solidified on the surface of that solution. And this is okay. The directions told me that it might solidify and become a solid, and that's perfectly fine. So that is not surprising to me, as long as I've read the lab procedure before coming into the lab, right? So I'm getting ready to transfer this with the solid into a separatory funnel, add some methylene chloride, and begin to extract the organic that's out of this water right now.
Okay, so this helps ensure that my alkane really does fully separate, but it also helps ensure that my temperature is suitable for the extraction solvent, which is methylene chloride, that's going to come next. So in the ice bath, toward the end of this process, I stopped it at 120 p.m., and that was the final temperature of the solution in the ice bath once I pulled it out of that beaker. All right, so now I've got this opportunity to remove the alkane that I'm physically seeing solidifying on the top here from the aqueous solution that's also there. So I've got this aqueous mix and this organic mix. It's forming two separate layers. I need to separate those two layers, so therefore the lab tells me to separate it using a separatory funnel. And this is one of the reasons that we do that. It's the whole reason that we use a separatory funnel. That's why we call it separatory in the beginning. All right. The only thing is that I'm going to have a proper solvent. Okay, and a proper solvent is going to have to go in and grab that alkane and pull it out of that aqueous solution. But the proper solvent also needs to be very volatile, which means that it should easily evaporate on me. I don't want to pick a solvent that I'm going to have to heat up with a tremendous amount of heat in order to drive it off, just so I can have my alkane that's left over. If I can pick a solvent that will grab the alkane, remove it from the aqueous solution, let me set it on maybe a hot plate on a really low temperature and let it evaporate off completely very easily, then this is a perfect organic extraction solvent for me. And that perfect organic extraction solvent is methylene chloride. All right, so methylene chloride, you can see the label here. We used Fisher Scientific, that's the company name. And then the lot number is 103387. However, methylene chloride is a common name for this substance. And it's one of those weird reasons that we do common and IUPAC names both in a chemistry course, because you'll never know what you'll see. And the real IUPAC name of methylene chloride is here on the side, and it's called dichloromethane. All right, well, we abbreviate that with DCM, dichloromethane. That's what that stands for. So whenever we use methylene chloride in a lab, we're really using dichloromethane. And dichloromethane, because we're lazy, we can abbreviate it with DCM, and that's perfectly okay to do. All right, well, the IUPAC name gives me a very clear understanding of what the structure is like. Well, methane is one carbon, and then that one carbon will have 4 bonds, and it looks like 2 of them are to chlorines, dichloro, right? I'm just going to write them opposite of each other. No big deal. It's all the same. And then the others are just going to assume to be hydrogen. So there's dichloromethane. So just by the name only, I can already interpret what that structure is going to be. Now, the problem here is that methylene chloride is a great organic extraction solvent, but it's also carcinogenic. So I don't want to be breathing this stuff in. I don't want to be absorbing this stuff through my skin, because it is somewhat linked to cancer, studies have shown in the past, and it's one of those things that we do want to pay attention to when we begin to use that in a laboratory setting. So I need to be able to use this methylene chloride, and I'm going to pour some of that methylene chloride into the separatory funnel along with the clathrate. All right, so here's the transfer of the clathrate first. You can see some of the solid remnant that's left over in the beaker. I'm going to transfer that over. The lab tells me in order to transfer this residual stuff over, use methylene chloride in order to do that. So I took some methylene chloride, I squirted it inside of this flask or this beaker, and then I gave it a good swirl, and then I dumped it out into the separatory funnel. So here's that methylene chloride, swirl, 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 transfer it over, and what I have left over is this. Well, I'm getting ready to do that again. So I'm going to add more methylene chloride to this beaker. I'm going to give it another swirl, another 10 milliliters, and then I'm going to add that into the separatory funnel as well. So here's rinse number 2 from the bottom view. And I felt really good after that second rinse of the 10 milliliters of methylene chloride. All right. I'm then going to go to the balance. The directions are going to tell me that this Clathrate with the methylene chloride is going to go into a beaker. I'm going to have to evaporate that off so I can be left with just the alkane only. So that also means that I need a masked beaker if that's where my product is going to end up being. So that's what this process is going to be. So I go back to my balance, 0.0000 grams. I then place a beaker onto that balance. I get 68.4244 grams, and this is what my methylene chloride with the alkane will go into. All right, so there's the beaker, empty beaker for that process. The lab directions tell me to take 40 milliliters of methylene chloride, so that's what you're seeing here. I used a little bit more. And then it told me to wash it in 2 portions. All right, so the first portion is going to go in. I'm going to say about 20 milliliters in total, about half. And what you see in the separatory funnel are 2 layers that form. A cloudy one on top, and then a more clear one on the bottom.
So what you're seeing here in the separatory funnel is 2 layers, and we're going to separate them. That's why we call it a separatory funnel. So we get a layer at the top and a layer at the bottom. The layer at the top is very cloudy. The layer at the bottom is very clear. I'm going to open up the stopcock here and let it slowly drip, 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 drip into a beaker that's going to sit down below. I'm going to then add another portion of methylene chloride or dichloromethane to the layer, and I'm going to do another wash and another drain just to make sure that I do extract all of the organic out of the aqueous phase, and that's what this is all about. So there's the separatory funnel setup. The problem here is that people are not patient. They do not allow these layers enough time to separate from each other before they go on to the next. So because I'm doing it, I'm going to wait another 10 minutes and just let it kind of hang out, and I'm not going to rush it because as a lab group together, we want good data, don't we? So that's what I'm going to do with the separatory funnel.
Okay, so that gives you an image of what this begins to look like in the separatory funnel. I did wait, and that's normally what I do. I do wait for, you know, a good handful of minutes before I begin to drain and extract anything out of separatory funnels. Here's a couple of pictures of how to properly use a separatory funnel. So to the left, you're seeing me turn the separatory funnel upside down. My finger is on the stopper up here at the top, though, right? So that way it doesn't, of course, dump out and get liquid everywhere. And there goes my product. But methylene chloride is very volatile, and it builds up pressure. So one of the things I do is that I rock it. So I turn it over, and then I turn it up the right way. And then I turn it upside down, and then I turn it upright. Well, when I turn it upside down, sometimes I'll grab the stopcock, and I will slowly turn the stopcock open. And I have this pointed straight up in the air. So that way, if there's pressure that gets built up, that pressure can escape and out of the funnel, and then I'll just close the stopcock back and turn it back upright, and then allow these 2 layers to separate on me. So that's what I'm doing in these pictures. I'm rocking the separatory funnel, and that's what we call that. Okay, so over time, I see this separation get a little bit better, a little bit more defined, and I begin to drain off that bottom layer. That bottom layer is my methylene chloride layer. This is my DCM layer. I know this a couple of ways. I can use density in order to do that, or when I add my methylene chloride, I can see which layer gets bigger. Does my cloudy layer get bigger, or does the clear layer get bigger? And I honestly see the clear layer getting bigger when I add the methylene chloride in. So I know that that is my methylene chloride that is extracting my alkane out of that aqueous solution. All right, so I'm going to slowly drain it. So I open up the stopcock here, and then I drip, 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 drip until I get closer to the cloudy layer. Now notice it's not as cloudy down here, and that's because this is not my final extraction. Okay, they tell me that I'm going to have to wash it for a second time, and that's exactly what I do. So I just go to a graduated cylinder, pour some methylene chloride in it again, and I just eyeball it. And I use about 20 milliliters of that 30 that you're seeing in the picture into the separatory funnel. So I don't add it all, but it gave me a way to easily pour methylene chloride from that big amber 4-liter jug into a graduated cylinder first, and then allow me to transfer it over into the sep funnel. Okay, so second portion, second extraction, I do this step all over again, and this time I do drain everything clear that I am seeing after that point. Okay, so the next step is I need to take that methylene chloride and now I need to evaporate it off. Good news is that this evaporation happens at a very low temperature. Okay, so meaning I can put this beaker on a hot plate or in a hot water bath, and I can barely just crank up the heat to it, and it's going to be enough heat to evaporate off the methylene chloride. Sometimes I can actually accomplish this just by holding the flask in my hand. So the heat that's generated from my hands could be good enough to get this stuff to start evaporating off on me. And that's what you're seeing me do here in this picture. So hot water bath in the beaker. I've put that beaker on a hot plate. I've turned it up about halfway. And then I see an inner beaker, and the inner beaker is my methylene chloride with the alkane. Now, the methylene chloride has a boiling point that is super, super low. And the alkane, depending on whichever one I have, has a boiling point that is very high. Okay, it's 100 or more. So there's a big drastic difference here. And that drastic difference is also going to let me know that I should not make this go to the boiling point of water. If I do, I have the chance of driving off that alkane that maybe I want to keep. So as soon as I see the boiling of the methylene chloride at the low heat stopping, then I'm going to take this off and I'll let it just cool to room temperature at that point. All right, so I've got another video here of this process, and this is the evaporation process of the methylene chloride. So I have my extracted organic right now in another hot water bath. Methylene chloride evaporates at a very low temperature, and my organic is an elevated temperature. So I've put it in a hot water bath, not directly on the heat plate. The reason I want control of this again, and I only want the methylene chloride to evaporate off. So if I put it directly on the heat plate, there's a chance that it will get so hot that it will also evaporate my organic as well. So here I'm ensuring that with the water, it's not going to go over 100 degrees at this point. So I'll just let this continue to bubble and boil, as you can see down here in the bottom of the beaker, until I don't see that any longer. And then when I don't see that anymore, I'll take the inner beaker out and I'll let it cool on my countertop, and then I'll take it to a balance to get a weight. Okay, folks, we're almost done. So that evaporation step began at 1:54 p.m. You can see the time stamp up here at the top that I recorded. And then I stopped that boiling process at 2:02 p.m. So you can see it didn't take very long for all of that methylene chloride to evaporate off and out of the beaker. What I have left over right now, this is the alkane, and it's one of those two alkanes that I started with in the very beginning. I just got to figure out which one it is. Well, I need to let this beaker cool, because part of the lab directions are going to tell me to get a mass of this. How much did I recover? How much did I reclaim? Out of all of those transfer steps that we did, out of the crystal formation, the funneling, the washing, the transfers, how much alkane do I have left over in the very end? And if I look at this, I feel pretty good about myself. And the reason is because I physically can see that layer. If this was just a smear, then I would be, uh-oh, I didn't do a very good job. And you could have ended up with a smear. And that could have been due to not catching the extra filtration that came through and precipitated out in that filter flask. Look at how much crystal that was there that precipitated out. So I'm going to go back to the balance. I'm going to tare out the balance, and that's what you're seeing in the picture. I then take that beaker with the residue, and I put that onto the balance, and there... excuse me, and there's my number for that mass, 70.1080. Notice that this is cooled to room temperature. I can hold it easily with my hands. And quite honestly, folks, whenever I use methylene chloride that evaporates off like this, I leave this beaker on there and I wait for like 5 minutes and I come back to see if my mass has changed any at all. If it has, then that means methylene chloride is still there and it's still evaporating off. And what I did not see was a fluctuation in the mass. So I did leave it there. I came back to it just to make sure that that was a legitimate mass, and it was. All of the methylene chloride was evaporated off. I was not seeing a lower mass that kept popping up on my balance. So 70.1080 is going to be the mass of that beaker and that Alkane product. All right, so next I need to identify what this component is. So in the lab directions, they're going to tell me to use a infrared spectrometer, and that's what we're going to be getting ready to use at this point. The infrared spectrometer that we like to use in our laboratory is an FTIR, and the F stands for Fourier, and the T stands for transform. So Fourier transform infrared spectrometer. It is a better instrument than infrared. It does my job quicker. It does my job better. It is made structurally different than a normal infrared is. And the loading process on this FTIR is way better as well, and you'll see that in just a second. Here's the FTIR instrument. We have the instrument manufacturer from Shimatsu. Shimatsu is a Japanese company, and they specialize in analytical instrumentation for a laboratory. So Shimatsu is going to be the company name. FTIR is going to be the instrument that we're going to be using. And one of the first things that I want to do is turn the instrument on. So there on the bottom right-hand corner is my flip switch. So I'm going to flip that instrument on, and this will initialize the instrument so it can start talking to my computer. The computer has software on it that makes this machine operational, and that software is called Lab Solutions Infrared, or IR. So I'm going to double-click Lab Solutions IR. The reason I'm showing you these steps is that your lab notebook is going to require you to write directions on how to use the equipment. So you want to put that into an appendix, so that way if we ever use this again, you can just simply refer to the appendix and say this is where you can find those directions. All right, so Lab Solutions IR, I'll double click. When I do that, this box shows up on the screen. It's asking for a ID and password. We do not have our software password protected. So we just hit OK at this point, and it bypasses that screen, and this shows up on the computer. I've got a couple of options here that I can do. But one of the major things that I always do with this instrument is look at a spectrum. So I need to obtain a spectrum for this compound that we have in our beaker. I need to know what it is. So I'm going to click the spectrum icon. When I do, this screen pops up. This is the main working screen, or part of it. And the reason I'm showing you this first is because we have to initialize the instrument. So I'm going to click this instrument button, and when I do that, a drop-down menu happens, and I click Initialize. So this allows the computer software to begin talking to my FTIR instrument to make sure that they are operational with each other. After it initializes, it just takes less than a minute. I will see 3 big green buttons that show up over here on the left-hand side of my computer screen. One is Background Scan, one is Sample Scan, and one is Monitor. All right, so we need a background at first. This is like tearing a balance. So I need to tear it out before I put my component on it that we want measured. Well, in the cabinet, we have what we call an ATR attachment. The ATR stands for Attenuated Total Reflectance. This is a way that I can easily load up my sample on this machine and get it to analyze. So I'm going to take out the ATR attachment. It runs off of a diamond. That diamond is about $18,000 with no exaggeration. It's about $18,000. And this attachment goes on to the machine, which is another $20,000 to $25,000 as well. All right, so here's the ATR attachment up. This metal plate is where the diamond is located, and the diamond is just right there in the center. So that is what costs the most for the ATR attachment. That's also where the sample is going to be dropped onto the surface of that diamond so this machine can do its job. All right, so on the inside of the machine, this is what it looks like. Open up the front cover or the front door of the instrument. That's this big gray lid that you see right there in front. So I take this, I open it up. When I do open it up, the ATR attachment fits nicely on the inside, and there's a screw here in the front that I just tighten so that way it doesn't get loose and it doesn't fall out if I get excited. And then I go back to my computer screen and I hit background scan. All right, so when I hit background scan, this is its way of tearing itself out. All right, so this is what I begin seeing on my computer screen, and this is very normal. It looks just like a bunch of lines, doesn't it? And I know that it does, and I'm not asking you to know what those are, but this is a very normal image of a background scan, which means that my instrument is working the proper way. All right, so what I have here is a video. This video, though, is based on another lab that we did with the FTIR in another course, and we made moonshine. So with the ethanol-based lab, I gave a little bit of intro about tearing out the balance and getting the machine to run, and that's what you're going to see here. So keep in mind that this is going to be ethanol-based and not alkane-based, but they both work the same way.
If you've had one of our classes before, you know what this instrument is. This is our FTIR instrument, which stands for Fourier Transform Infrared Spectroscopy. So I'm getting ready to put a drop or two of my distilled ethanol onto this instrument, and hopefully this instrument will tell me that it is ethanol before I decide to drink it. All right, so this is just a way that we can identify a compound in a laboratory. This instrument is connected to a computer. You can see that it's running something right now, and the only thing it is running is a background scan. So I'm not running anything on it at this point. It's just really the ATR attachment, which is what you're finding inside of the instrument. And that ATR attachment right now is blanking itself out. So think of this as a tare function on a balance. Once this gets finished, I'll put a drop or two of my sample onto the instrument, and I will use the software in order to data match it. So more pictures to come, but this is the FTIR instrument that we will be using to identify, hopefully, the ethanol that I have made in the lab.
Okay, so again, that was an ethanol-based description there, but Alkane works the same way. The blanking process doesn't use anything on that plate. No water, no nothing. So this is just completely cleaned off. There's nothing on it at all, and we are tearing out the machine at this point. All right, once it gets finished, we then need to go and we need to add our component to it. So up here at the very top, I'm going to go back into measurement. That takes me to the main screen that we saw before with the three big buttons, and this time I'm going to put a drop or two of our sample on it, and I'm going to hit sample scan now, not background scan. Okay, so a couple of drops of my Alkane goes onto the ATR plate with that diamond, and then I'm going to scan that sample.
Guys, what you're seeing in this image is our FTIR instrument, which stands for Fourier Transform Infrared Spectroscopy, or spectrometer. Right now, it's measuring our sample that we have taken from our Alkane Clathrate, and it's measuring that sample's fingerprint. So I've got a few drops on that metal plate that you see in the center, and then that instrument is connected to our computer, and that computer is going to be here. And what you see on our screen right now is the fingerprint for that particular molecule, and we call that the IR spectra. Something that you'll learn a little bit more about in an organic course, typically in the second semester, not the first. So this instrument is scanning this 45 times, and it's doing an average. When it gets finished, I'll use the database in the software, and it will cross-reference what I'm seeing on my computer screen right now to a matching database spectra. And whichever one it comes out to be the closest with, that's going to be the compound name that will pop out onto the computer screen. So it helps me identify an unknown liquid or an unknown solid based on something that we call the IR spectra. So this has about 30 seconds left to run. I'm going to stop the video right now. Nothing really exciting is happening on the screen, but it gives you an idea of our FTIR instrument that we have in our laboratory. So there is a modernized version of an infrared spectrometer.
Folks, another thing I want to say is that as an undergraduate, you have very few chances to use equipment like this. Whether you're taking this class at a community college or a four-year school or a university and so forth, you just never really get a chance to see the real analytical equipment and real science at hand, and this is one of those examples. So if I go back after this is scanned, it goes back to a screen that looks like this up at the top, and see this binocular icon up here at the top right-hand side. This is called search, and then this is going to let me search the database of infrared spectra that this computer software has stored in its memory. So I'm going to hit search, and then I'm going to spectrum search the compound, and the database is going to match up my infrared to the best possible one. And this is what shows up. All right, so when I hit search, it's going to, and it finds a report that it closely matches to, and then number one is dodecane. All right, so dodecane. Do means 2, and dec is 2 or 10. So this is going to be 12 carbons in total. I didn't use 12 carbons. I had one that was 16, but I didn't have one that was 12. And then the 2,2,4-trimethyl pentane, that was 8. Well, here's the thing. 12 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, or 13, 14, 15, 16. I mean, you can kind of imagine that that's pretty close, but it's not perfect, is it? Dodecane is 12 carbons. I had either hexadecane or 2,2,4-trimethylpentane, not dodecane. But as I scroll down this list, it gives me the top 20 choices. And in the top 20 choices, I see hexadecane that shows up. So it is there. It wasn't the best match for reasons. That's because these things are so super close in infrared spectra that sometimes this equipment gets confused a little bit. I mean, they're both straight chains, they're both carbon-based, they're both hydrogen-based, they're both hydrocarbons, they have no functional groups on them. They are structurally very, very similar, except one just has a fewer carbons than the other one, right? And it's measuring the fingerprint of these compounds as they're coming through, and those fingerprints are very, very close. So hexadecane does show up. It's there. So I feel really good that this is the alkane that my urea has captured at this point. All right. One thing I also don't want you to forget is always clean the plates when you're done. So we clean them with methanol or acetone. They make very good organic solvents. So methanol, acetone, maybe both. Just give this plate a very good wipe down because we want that $18,000 diamond right there to stay clean. All right. Now I'm not really finished yet. The directions don't tell me to do this in the lab, but I am going to do this in the grade sheet, and I need to confirm it. I need to confirm that that alkane is hexadecane, and I'm going to do that using refractive index. All right, so a refractive index instrument looks like this. We've used this maybe in some of our other labs if you've had classes with me before. If you've never used this before, though, the refractive index, it measures how the bond, it measures how the light bends through the bonding of the molecules. So we have a prism, and that prism has a drop of liquid on it, and the light from a lamp is going to be directed onto that drop, and this liquid is going to bend the light a certain way. Okay, so the way that it bends the light, that is really referred to as the refractive index, or the IR. I always tell people to imagine a swimming pool, and looking down on someone in a pool, the top half does not match the bottom half, right? So there's refractive index at play, because water has a refractive index as well. It's bending the light, it's bending the image, so it slightly distorts it in the swimming pool. So this is the refractive index, and this video is going to tell you a little bit about that refractive index instrument, if you've never used one before, maybe you haven't.
Folks, this is the refractive index instrument, and I'm getting ready to run my cuts on the refractive index, or refractometer is another word that we call it. Alright, so the way that I use this, just in case you've not used it before. Okay, so here's my prism. I'm going to open the prism up. I'll put 1 or 2 drops of my sample onto the prism that's been cleaned with acetone or methanol. I then close this prism back, and I'll take this lamp in the front and I'll raise it up to the prism. To the left hand side, I'll see a flip switch. I'll push down midway. That turns the light on. I'll look through the eyepiece. When I do, I'll see a large light and dark area to show up. I want that midway, half light, half dark. When I line it up the proper way, I'll go back to my flip switch, I'll push down, and then a meter will show up in the top. Once the meter shows up, I'll read the number that is displayed, and then I'll move on to my next cut. Folks, I've got probably 15 cuts here plus a pot sample, so I'll be at this refractometer quite a while.
Alright folks, so toward the end of that video, a pot sample was not what you thought it was. A pot sample was from a different lab that I used to introduce the refractive index with. This refractive index is used for multiple things, for multiple labs, and this is just one of them. So when I did that first demo, it was on something completely different. So pot sample was from an actual bowling pot sample, not pot. Alright, so what you don't want to see here through the eyepiece is something that looks like this. I mentioned a light half and a dark half. This is bad. I can see the light and the dark, but the dividing line in between them is very smeary, right? It's not well defined. That's also not well defined either. And then I can adjust this. The way that I do that is I go here into the fine adjustment tool in the front, and I just turn this left or I turn this right. Okay. The reason I'm telling you these directions is because the grade sheet's going to ask you for detailed steps on how to use a refractive index or refractometer, and this is how we do it. So if I see an image like this that's very blurry between the light and the dark half, and maybe an image like this that's very blurry between the light and the dark half, notice they're different colors, which means that I've went too far one way or the other. I'm going to take the fine adjustment tool, I'm going to slightly turn it left or right until I end up with something that looks like this. Here is a very good defining dividing line. Okay, so the light half on top, the dark half on the bottom. If they are not perfectly matched up with the crosshairs, which is right here, okay, that's where the dividing line should be, then I need to move that line up or down. And the way that I do that is using this big huge knob over here on the right hand side. So I slowly turn up or I slowly turn it down, and this will get the dividing line to move up or to move down. And it's my job to get this in the very center. So I'm going to take the Alkane Clathrate that we just extracted. I'm going to put a drop or two of that on the refractometer, and then I'm going to adjust the dividing line where it's in the middle at the crosshairs. It looks very well defined to me, no fine adjustment needed. Then I take that flip switch and I push down. And when I do that, this is the meter that shows up. All right, so how do we read this number? Well, this is 1.430. This is 431, 432, 433, 434, 435. That would be 436, 437, 438, 439, 440. All right, so those are what the taller lines mean on that meter. But notice that this line that goes straight up, right, that's the number that I need to read. Where does that cross? It's kind of in the middle, isn't it? This is 430, 431, 432, 433. This is right in the middle, and you see that other short little line right there. So the way that we would read that number is 1.43, and again, that's 30, 3132, and this is halfway to 433. So that is 4325. Each one of those lines are 0.0005 in increments, and that is how we would read the refractive index number, or the meter. All right, so that's the reading for my clathrate, the alkane that came from the clathrate. So then I go back and I read the 2,2,4-trimethyl-pentane as well, just to match it up with stuff that we used. So here is the initial. I flip the switch down, and here is my readout. You can make that reading as you see fit. You can pause this video if you need to in order to read it, but there you go. And then I go to Hexadecane, which is what the FTIR told me that this stuff was. And then I read the Hexadecane, and there is the readout for Hexadecane. Again, you can pause that and make your reading as you see fit. So this just gives me another confirmation of whether or not the FTIR was telling me the truth. It's something that we always do in a lab. We never settle with just one. We always try to incorporate more than one test whenever possible. But folks, this is the Alkane Clathrate lab. All right. So I babbled for 1 hour and 40 minutes plus over a simple little extraction technique that was done with 2 alkanes and some urea. And that's all it was. All right. But as you can tell, there were a lot of steps involved. There was a lot of cooling. There was a lot of transfers, 2 instrumentation types of tests toward the very end to confirm what I actually had. And that is really what started to eat away at this time. All right. So good luck on the lab write-up. The grade sheet is going to be posted for you, so that way you can take this grade sheet, adapt it, write into your laboratory notebook what you should be writing in, observations and times and everything else. And that way you can wrap up this lab, turn it into grade, and get an easy 100, because it should be 100, right? Okay, so hope our lab date is good, and I hope you enjoyed your time with me. And I'll see you next time, I guess, for the next lab that we'll do together.